Okay, so this is my first video. It's going to be pretty short and sweet. This is my first video for the AC portion. It is week 1 of the second term of AC/DC, so we're getting into alternating current. We've been dealing with circuits in direct current. And the difference between alternating current and direct current is obviously the source of power. The source of power for alternating current is something that is usually supplied to us by a utility. Somewhere there's a turbine spinning, water's pushing it, or air is pushing it, or a coal plant is pushing it, or nuclear power is creating steam that's pushing a turbine that runs and in a circular motion creates electricity. Your book has some really good graphics on this, pages 396 and 397, about how that circular rotational force creates alternating current. The thing about alternating current is it's constantly changing. The flavor that we use here in the United States is 60 hertz. And what that means is that 60 times a second, or those of you who've been in the military or have some other electronics background, 60 cycles, it's called. 60 times a second, the voltage goes from 0 to its high in one direction, past 0 again to its high in the other direction, or low, depending on how you're looking at it, and then back to 0 again. And we're going to graph that. But that happens with the voltage, and it happens with the resultant current of anything being pushed by that voltage. So we can say we have alternating current, which is voltage going up and down, pushing current, again, the speed of the current, the flow of the current, the amount of current in amps, changing constantly. But we tend to talk about those values as solid, even values, and we call those RMS, root mean squared values. If you've got a good multimeter, your multimeter measures AC, voltage and current, in RMS, root mean squared. We'll talk about that a little. I'm hoping that you guys have watched the other videos. There are, I think, 2 other mandatory videos to watch for this week. One of them has got my favorite British presenter of physics, and in part of her electronics or electrical stuff, she talks about root mean squared, gives a little bit better explanation than I'm going to be able to. There's some calculus involved in that I'm not going to get into as to how root mean squared is figured out. The good news is we don't have to do any of that math in this class. When we're measuring AC, we're going to use RMS values, period, end of story. And I'll explain why. When we're measuring DC, we use DC values, which is an exact absolute value. We'll talk about that in the graph a little bit. Go ahead and look at pages 396 and 396 and 397 in your book. On 396, it shows a rotational generator. So essentially, I'll mirror that a little bit, what it's showing in 396. But if I have a couple of magnets and I have a wire spinning across these, so there are lines of magnetic force. And the book talks about this a little bit between those magnets. And if I cut those lines of magnetic force, say I have something spinning, I have a loop of wire. And that loop of wire looks like this, and that loop of wire is going to go like this around this thing. If I'm swinging right up here at the top, as close to parallel as I'm ever going to with the lines of flux, I'm generating very little voltage because I am not cutting very many lines of flux over the same period of time. But when I come down through to here, say to this point, now I'm cutting across lots of lines of flux because I am now moving perpendicular to those lines. It's the difference between if I'm riding down a street with the lines in the street, I'm not crossing too many of them, or if I'm crossing a street and I'm going across all of the lines in the street. When I cross all of those lines, every line I cross is inducing voltage. This is part of, we talked a little bit about inductors, and inductors induce a voltage. That's what's going on when they're generated. We don't need to get too far into this, but the cool thing about this is this is the reason that when we talk about AC current, we graph it like this. Now you guys are all familiar with X and Y axes on graphs, and again, this is just a model. This is just a way for us to understand and think about what's going on with the voltage and the current. Again, there's that great quote about all models are wrong, but some of them are useful. For extra credit, find out who said that. There's another really good quote I heard this weekend that essentially says the same thing. He said, a fellow said some time ago, he's dead, he said, all art is a lie, but the good art tells us the truth. So hopefully this is a good art. Find out who said that for me too for some extra credit. So all art is a lie, but it tells us the truth, I think. And I may be mangling that quote a little bit. X and Y axis, right? So I've got time going this way, and I've got some sort of magnitude going up and down my x-axis. I have that right? X is this axis, and Y is this axis. If this is a graph. So if I start graphing the voltage, and I'm producing like close to 0 volts right here. Now remember, this is now. So time equals right now, and this down here on my graph is sometime in the future. And then this is, say, let's say voltage. So this is voltage up here, and this is voltage down here, the other side is 0. This is 0 volts. So we can go above 0 in one direction or in the other direction. I can have voltage either way. Remember, voltage is a difference between two things. So I can have a positive voltage compared to 0 or a negative voltage compared to 0. And in our world, it doesn't matter which is which, except that they're opposite from each other. So I start graphing this thing, and right here I've got 0 volts. But I start moving a little bit, and I start getting a few more volts as I move like here to here to here. Remember, because this thing is swinging in time, and this axis is in time. And when I get all the way to here, I'm getting the most volts I'm going to get. And then I start cutting fewer and fewer till I'm all the way down to parallel again. And if I graph that out, it's going to look like this. Because when I start swinging the other direction, now I was cutting across my lines of flux that way. Now I'm cutting across my lines of flux this way. So the voltage that I create by cutting across those flux with this conductor that's spinning between these two magnets, which is one of the many ways a generator works or a turbine works, it's going to create a voltage in the opposite, which is why I started drawing those there. So essentially I have graphed a bunch of dots that when I put together look like a sine wave. And that's all a sine wave is. It's just a model of, an explanation of what's going on with the voltage over time. Now, the voltage that the frequency that we use, the flavor of alternating current that we use in the US is 60 hertz. There are a couple of cheat sheets I want you to download from your Moodle. One of them talks about frequency, one of them talks about inductors, because inductors are the first thing we're going to get into hot and heavy this term. 60 hertz simply means that this, what I've drawn here, happens 60 times a second. So this all the way to here, going from 0 to its high point, to its middle, to its other high point, to 0 again, that happens 60 times a second. We call that one cycle. And that cycle can be divided into portions that are degrees, just like a circle can, because it's a circle that made that. So, I can take any circle and mathematically divide it into 360 pieces that we call degrees. There's another thing you can do with circles. You divide them into 400 and it's radians. We're not going to use radians. We use degrees. So dividing a circle into 360 degrees, you guys know, well, that's 90 degrees, that's 180 degrees, that's 270 degrees, and all the way back up to 360 or 0 again. I can divide a circle like that. So if I take those coordinates on this, I can say, well, here I am at 90 degrees, and here I am at 180 degrees, and here I am at 270 degrees, and here I am back to 0 or 360, whichever way you want to think about it. So I can divide up my sine wave, each cycle, into 360 chunks that we'll call degrees, and that correspond exactly to the rotation of the generator that's creating this voltage. So that's important because we're going to use degrees on a sine wave this term. Again, read the material in your book. It's really, really a good chapter in this book. Not every chapter is good, but this one is. There's some stuff that we aren't going to be worried about and we're not going to be caring about. It gets into rectifiers, things like that. Read it. It's great to know, but we don't care so much. The other thing, let me look at my notes to make sure I didn't skip telling you guys anything. Let's talk about RMS a little bit more. So, I said that when I'm looking at this, I'm getting up here to my top, the most voltage I'm going to get generating in this. And that'll be some number, it doesn't matter what number that is, but that voltage there we call peak voltage. Obviously it's peak, it's the top. And this is also peak voltage. And if it's a sine wave that works like most sine waves with an equal generators working correctly, this will be as far from 0 as this is from 0. This will be the same number as this is from 0. And so it'll be an equal-sided sine wave. The magnitude in this direction will be the same as the magnitude in that direction. In this case, we're going to call everything on the x-axis the magnitude. When you work in oscilloscopes and things like that, you have to think in those terms. This is time, this is magnitude. So that's peak voltage. So if you're into electronics, there's some things that you're going to hear voltages called. You're going to say, well, what's my peak voltage of that sine wave? And that's more important when you're doing things like square waves, digital waves, you know, where instead of having a nice sine wave like that, things are switching off and on, and you're getting a shape like that. Then you'll also have something called peak to peak. So say this peak voltage was 169 volts. Peak to peak is going to be twice that. So peak to peak is going to be whatever 169 twice is, right? Well, let's see, 160 twice is 320, 338. Is that right? I may or may not have done that math right, so don't quote me. But that would be my peak to peak voltage. Now my RMS voltage, and we talked about that a little bit, the RMS voltage is going to be voltage peak times 0.707. Again, you don't ever need to do this math. When I give you AC voltage, AC current, it's already going to be in VRMS, voltage root mean squared. And what the root mean squared is, and this is my limited understanding, because I'm not a mathematician, maybe you've noticed that, but my limited understanding, the root mean squared is essentially the area, remember, because this is my voltage, and so my current is going to reflect that, right? My current, especially in a resistive, is going to be at the same cycle. So as my voltage pushes my current, if I also graph the current on here, say I do it in another color, my current will match maybe not the magnitude, depending on what I've used for my gradients, but it will match in phase. And so I'm going to have power. Remember, power is volts times amps. Everything underneath both of these, when I have, I'll use red again, when I have both voltage and current, I've got power there, and I've got power there. And I can figure out how much that power is worth, how much power I actually have over time, because remember, this is going on and off, over time with calculus by figuring out what the area underneath that curve is. It's one of the things they do in calculus functions. They figure out the area of something underneath a curve. We don't need to do that because somebody's already done the hard math for us and said, well, that value actually equals 0.707 of what it would be if it was DC. So if this was my DC, right, boom, right there at 169, if I multiply 169 by 0.707, it's going to give me, magically, 120 volts. So the 120 volts that you get out of your electrical receptacle at your house, or that you measure from neutral to hot in a standard panel, that's actually moving a sine wave up to 169 volts in 0, 169. But we don't get the value of 169 because we want a number, and RMS is the number that allows us to continue to use E equals I times R. And R equals E over I. All of my Ohm's law formulas, as well as Watt's law. P equals I times E. In AC, these only work if we're talking RMS values. I is RMS, E is RMS. Now R doesn't have an RMS, R is R. Resistance is resistor. Power, I don't know that power is RMS either. Let me erase that because power is already taken into account this RMS and this RMS. So root mean squared, it's just the flavor of voltage measurement that we're going to use. And that's why. There's a really good video on this. Again, the woman, the British woman who does the videos for PBS, please watch that because that's going to give you some better understanding of what's going on with root mean squared. So that was more than I wanted to talk about on that. We talked about hertz. The book talks about wavelength a little bit. Wavelength is a thing that people who are concerned about communication are more concerned with than we are. We really have only one frequency. Our frequency is a very small wavelength. I'm never going to ask any wavelength questions, but you do need to understand that wavelength is a physical distance that something can travel when it's traveling the speed of light and moving at whatever speed the frequency is. 60 times a second means that this thing happens 60 times in 1 second. So if I go 1/60th of a second, that's how long it takes for this to happen. And that's the same as 0.016 seconds, or 16, not point, 16 and change milliseconds, right? Thousandths of a second. That is the cycle length. That is not the wavelength. That is the cycle length in time. The wavelength is a physical distance measured in meters or kilometers. We don't care about that. We're electricians. We leave that to the radio geeks and people like that. But understand it's different. My cycle is 1/60th is my hertz, and it takes 16 milliseconds for that to happen. Every 16 milliseconds, this happens once. So 60 times a second, that happens. If you've ever gotten caught up in that shock, that's the frequency that you're vibrating if you've gotten shocked. So that's enough of that. I want to talk a little bit about inductors. And the first thing we need to know about inductors is, and this is going a little bit into next week, but that's okay. We've got this voltage law formula that we've been using, right? E equals I times R, and then R equals E over I, and every other variation on that. So we model that with this circle that I managed to keep up here. The eagle and the individual and the rabbit, right, in the circle. R is resistance. Resistance is actually only one part of a bigger concept. Everything that opposes the flow of current in a circuit, in electricity, is called impedance. And impedance, we use a Z for its symbol, and I don't know why. But you might have seen this in transformers. What's the impedance of that transformer? That's the internal resistance of the wire and some other factors. So that's impedance. Impedance is the bigger concept. Resistance is part of impedance. Impedance is made up of two things. Resistance, which we already know about, and that is when a resistor opposes the flow of current, creates heat. If you push current through a resistor with a voltage, you make heat. I mean, it does other things to the current and the voltage, but what it creates, or what it transforms that electrical energy into, is heat energy. When I have a component that reacts to the change in current or the change in voltage, that component is called a reactive component. And we have two types of reactive components. We have an inductor. An inductor opposes a change in current. And we have a capacitor. A capacitor opposes a change in voltage. In my earlier videos, I explained that a little bit. I started touching on that. The book will touch on it more. And we modeled the curve. When I put current on an inductor, there's a curve up until it's full flow. When I put voltage on a capacitor, there's a curve up until it gets to full voltage on the capacitor. Both of those things, when they're happening, are essentially resisting the flow of current. I know that a capacitor is voltage sensitive, but by its voltage changing, it's reducing, it's changing the ability of current to flow in that circuit. And it's only doing it because of the change in voltage. So both of those components are called reactive components. So X is reactance. So I'll write it over here, but I'm going to stand in front of it. X is reactance, R is resistance, and then reactance is made up of X sub L and X sub C. And I drew C up here already, I don't know why. X sub L, remember L is inductors. X sub C is the reactance because of a capacitor. So, when I go to my Ohm's law wheel, I got my E, I, R. Remember that R is actually Z. It's the impedance. And we're going to use that. Now, this relationship is a little bit more complicated than this. Resistance is in ohms. Reactance is also in ohms. But we're going to find out that if resistance is modeled like this as a vector, reactance is actually either modeled up or down at 90 degrees from that resistance. X sub L would be up here and X sub C would be there. So I know we've all been doing Pythagorean. This is why we're doing Pythagorean, because when we have a circuit that has either reactance of this flavor or this flavor, that reactance is not going to be in the same direction as resistance. And that may not, you may be saying to yourself, what the hell does he mean? It's not in the same direction. Well, that's going to become apparent. But for now, understand that all of these things make up impedance. And we're going to be substituting either X or Z off it into that formula, because we're going to have to solve for Z in order to find other values. And we'll use that Z the same way you've learned to use R. But that can become confusing to some folks. More on that as we go. That's it for this week. Please do the reading, watch the videos, and I will have a quiz up for you by 6 o'clock Monday. It's Sunday night as I'm writing this. I'm going to try and have it up sooner than that, but that's going to be my cutoff every week. I'm going to try to have a video up Monday morning, a quiz Monday night, or a homework, quiz homework. It's kind of going to be a hybrid of the two. The school is requiring me to have you guys turn in something via Moodle every week. Now, to submit to Moodle, please try to use your iPhone. Where the hell did my iPhone go? Try to use your iPhone if you've got one. I apologize. I know you don't all have iPhones. But if I take my iPhone, if you've got a computer and you've got a scanner, if you're one of the people that I've said, hey, your submissions are great, just keep doing what you're doing. You're doing terrific. If you're not, if you've had trouble and you keep sending me PDF files, you have to email or text me. On your iPhone, on mine, I've got a little thing called Notes. If I open up Notes, it allows me, there's a camera at the bottom. I open it up, I hit the camera, and it gives me three choices. Scan documents, take a photo or video, or your photo library. Well, I don't want my library, I don't want to take a video, I want to scan a document. And when I use this to scan a document, I'm going to go ahead and scan a page of this book right now. Boom, color. And when I hit that, it allows me, and it lets me pull little buttons around, it allows me to take that, I'm going to keep this scan. Boom. And now I've got a scan, and it's a PDF. And I could take that PDF and I could either dump it into a Word document and send my instructor the whole Word document, or I could use that PDF. And I can do this as something I wrote or whatever, but it's going to be a PDF and Moodle will let you upload to it. Thank you, Blake Pruitt, again for figuring out the Moodle thing, because we fixed it for the whole school based on what you told me and the link you sent me. So thank you again for that. The submission maximum is now like 400 megs. So please don't send me 400 megs. Some of you have sent me huge files. I don't know why, but it's tough for me to deal with. So if you can do it that way, that's one good way to do it. The other way you can do it is use a scanner. If you take a picture of a document, please just take a picture of the document. I've been getting these pictures of documents that are either shaded terribly, or there's a whole bunch of other crap in the picture along with them, or they're teeny. I can't see them. So we're all working on it. We're doing our best. Thank you very much. Text me, email me if you have issues or questions, and the homework/quiz will be up tomorrow night. Adios.